Good evening. Hopefully everyone had a good weekend and is ready for hang on a second. And is ready for another productive week. So we're going to knock out one today and then one tomorrow, and then we'll be done again, ready for our weekend. So weekends are always the fun part, right? But we work so that we can have a good weekend. So, all right. I want to talk about a couple things quickly. I think some people had some problems with the assignment, being able to get it in properly. So I've given a little bit more time. I still haven't started grading it yet, but I will probably do that after I get done lecturing tonight. So I take that under advisement. So some people I think have trouble because I only allow PDFs. That's required, and actually D2L actually lets me do that, which is really nice. So again, I do that not to be mean, although you might feel like it sometimes. But the reason why I'm doing that is because that is how sometimes things will be done in a business world. So just giving you a chance to practice your skills at that now. So that's in a setting where if you mess up a little bit, it's not going to cost you your job, and I want to be able to set you up for success after graduation. So that's part of it. All right, so then let's just jump into. I needed a little bit more time on chapter 2. That is. Let me back up, because there's a little bit more housekeeping I need to talk about, and that is assignment 2 is up. I put it up earlier today, and that will still be due on Friday at 5 o'clock. So, and I think I've got it set up now, so I'll continue to take those assignments as long as people want to continue to turn them in. So, but I guarantee you that I will not start grading it until 5 o'clock on Friday. So that's, again, my late policy, is that when I start grading it, that's when everything is late. So if you want an extension, you can ask for it all you want, but it doesn't really matter anything, because it's the same for everybody when I start grading them. So sometimes that's the day of, and sometimes it's 2 days later. So it just depends on my schedule and where I'm at for that. So most of the time I'll have them done by Monday. So that's just where that's at. So good. All right. So a little bit of things left to do in chapter 2. So I'm going to go back and review some of those things, and that is error detection and correction. So one of the things that's important in a computer system, right? We looked at some different representations for numbers and some different representations for letters or other characters. In fact, actually, when I use the word letter, what I mean is any character that's not a value. And when I talk about numbers, we're always going to be talking, at this point, I think we should be talking about binary numbers. Will always be binary. And then the other one is value. And in value, I'll always show that in decimal representation. And the reason I do that is because that's the way we usually think about when we talk about value. So a value is the actual value that I'm looking at. It's not the representation. It's not the number representation. So that's a little bit different there. Okay. And the number is actually the characters that make up the value. So it's a matter of communicating those two things. They in a lot of ways, we bind them together very tightly in our abstractions of life. But in this case, I want to make sure that there's a distinction between the two, because sometimes we use base 10, sometimes we use base 2. And when we're talking about base 2, I'll be using, those numbers are binary numbers. And what they equal to for value, I'll translate into decimal. And the reason for that is because all of us probably, hopefully, it'd be really nice if we did think in binary, but we don't. So most people don't anyways. Okay, so that's a little bit on that. Okay, so error detection. So one of the things is we need to be able, so we've got all these strings of ones and zeros, and they could mean, right, it could be a floating point number, it could be a series of integers, it could be a series of characters, it could be simply one character. Just depends on the system and the context. So context actually matters a great deal in a computer system. So, but how do we know that it's right? So in the old days, right, when they stored things on those old floppy disks, or in the really old days on magnetic tapes, actually like a tape recorder, you could put them in. I don't know if any of you have actually seen or used cassette tape, but that was actually used, the same cassette tapes that you can use to have music on or whatever, those could be used in computers as well. In fact, they were in the 70s and into the 80s. Really interesting to put it into your player that would play it and listen to it, because it doesn't sound like music at all. It just sounds like a bunch of... It's definitely different. It's weird. So, in any case, those sometimes have errors on them, right? Because, like a DVD, right? You might drop it, or you might have some kind of scratch on it, or some kind of a problem. Or I might send something over the internet, and somewhere's in there, something happens in the electricity of things, and one of the bits gets messed up. So we need to have a way to both detect the problem and correct the problem. And so the way to detect it, there's a lot of different ways to detect it and correct it, but I want to talk about one idea, and that the first idea here I want to talk about is Hamming number. Let me get this working right here. So Hamming, that's double M. Oh, Hamming distance. Usually we're going to use that with this. So let me define Hamming distance. Actually, I'm going to define it with an example. So let's take my favorite number, 101010. Okay, and I want to look, and I look at another number, 111001. So what I'm going to do, and there could be more zeros here, 0, 1, 1, 0. Okay, so there's a bunch of stuff out here. So the Hamming distance can only be looked at in the portion that's the same, that has characters, right? So there has to be characters in both numbers. So what I'm going to do is I'm going to look here, and I'm just going to count all of the spots that are different. All right, so that's different. 1. That's different. That's another one. We'll just go ahead and do dashes here. That's the same, that's the same. That's different. Another one here, and that's the same, and then all the rest of these are all zeros. So actually, if I really wanted to do that, I should probably fill those zeros in, shouldn't I? Because they're assumed to be there. Oh boy, this one's really bad. All right, so then there's another one, and there's another one. So then that's that. I'm going to slash across there like that, and then another one here. So that gives us a Hamming distance of 6. So we just count up how many bits are different, right, in the corresponding positions. Now this is really, really high and insane. This would never, well, it's possible for it to happen. So, but the likelihood of this happening is very low. In fact, actually, there's a certain amount that we know that computer systems are going to make mistakes. In fact, it's something like one mistake out of every 10,000 or 100,000 bits. That's a lot, right? So there's one bit somewhere is in there that's a mistake. So okay, no, insert a space, pull this down a little bit. There we go. Okay. All right, and then it just disappears. All right, so evidently I have to put something down here. Call it the bottom. I can delete it later. There. Give me some space here. Come on. That'll be enough. Okay. All right, so then we're going to talk about then Hamming code. Now, Hamming distance actually doesn't have anything to do with the Hamming code. I mean, other than the fact it's named after the same guy, probably. Hamming code. All right, so this is how Hamming code works. Let's take my favorite number. Well, then I'm going to add a couple digits to it. Let's add 2 more digits to it. So that's some binary number, and it doesn't really matter what it is. It's not important. Okay, so what I'm going to do is, first off, I'm going to count up how many there are here. Oh, I'm going to determine how many bits I need. And so parity bits. Let me write that. Parity. Back that up. Parity bit. And then I'm also going to have data bits. So one way to do this, actually a real basic way to do this, to check to see if this is, we could do a parity bit. We could just do a single parity bit, and we'll put it at the end. And so we're going to do odd parity, let's say. So then we count up the number of ones. If it's odd, we put a 0. If it's even, we put a 1. And we could simply do that. That's not Hamming code. That's just called a checksum. Okay, but in this case, what I do is position 1 or parity 1. That'll be in this first box here. I'm just going to draw a bunch of boxes. I don't know for sure if I'll have enough, so P1 and P2 are always, let me actually back that up. Get rid of these here for now. Oh, no, I'm going to leave that there. Okay, so P2. But what I'm going to do is I'm going to start numbering these boxes. I'm going to start from here. And I know we normally start from 0, but in this case, we're not going to start from 0. We're going to start from 1. Five, 6, 7, 8. How many bits do we have? 2, 4, 6, 8. So we know we need at least 8. But the first 2, 1 and 2, those are parity bits. And also the next one is 4. I'm going to call it, P4. That's fine. And then the next one's going to be P8. So how did I know that those are all? Because this is equal to 2 to the 0. This is equal to 2 to the first. This is equal to 2 to the second. And wouldn't you know it, this is 2 to the third. And so those will be our parity bits. And those will be the ones we're going to leave blank. So we're going to need some more space, I think, here. All right, get back here. So then we're going to call this data 1, data 2, 3, 4, and we need 8 of them, right? So we need 4 more out here. Let me go ahead and grab this. Hopefully it grabs that P. It did, okay. And move that over here. Back to this. So then we have 9 here, 10, 11, and 12. Okay, so then this will be D5. What's the next power of 2? 16, so I don't have to worry about that one. So then D6, D7, and D8. Then I know I'm done. Okay, so let's put these in. So 0 goes here, and then a 1, and then a 0, and then a 1. I'll skip the parity bit there. 0, 1, 0, 1. Okay. So then what we do, this is interesting, because what we can do is we can look at each of these, not including the parity bits, but we could take that position, so let's say position 7. So 7, if we put 7 into base 2 or binary, it would be 1, 1, 1. So 7 will be part of the 1 bit, the 2 bit, and the 4 bit, 4 parity. So it will be included in all of those. The 6 is 1, 1, 0. So it will be part of 4 and 2, but not 1. So that's how we can know what it is. But there's a simpler pattern, or at least I think there's a simpler pattern. So let's look here. All right, so this is 1. So what we're going to do is we're going to include ourselves. We always include ourselves. And then whatever P number we are, then we're going to get that many more characters. So there's only 1, so there's just going to do 1 character. And then we're going to skip 1, and then take 1, and skip 1, take 1, skip 1, take 1. What that means is the first place is all the odd positions. And so I'm going to do odd parity. So I'm going to do odd parity. And I'll kind of show you what that means. So what I'm going to do is I'm going to count all of the ones in positions that are odd in here. So there's 3, that's a 0, so that's none. Then we have 1, and then we have 2, nope, and nope. So we have 2. 2 is even. So we're going to, because we are including ourselves here, we're going to go ahead and put a 1 there because that makes it odd. So now in the odd positions, there is an odd number of 1s. It's odd parity. Okay, so for 2, we're going to start with 2, and then we're going to get the next number, and then we're going to skip 2, and then do 2, and then skip 2, and then do 2. So 2 goes like this. Those 2, skip these 2, skip those 2, and then these 2. And if I broke each one of these down, in the second position, there would be a 1 in the binary representation for each of these numbers. All right, so let's look at these. We've got 0, 1, 2, so 2, which means then I want to make it odd parity, so I'm going to make this 1, so now we're up to 3, and now we're good. So now I bet you can figure out for 4, we're going to start here, and we're going to go 1, 2, 3, 4 numbers, and we're going to skip 4, 1, 2, 3, 4, and then we're just going to get this 1, but we would have got the next 3 if there was the ability to do that, if those numbers existed. Okay, so let's count them. 1, 2, 3. Aha, this one's odd already. So now that's a little different. So we're going to go ahead and put a 0 there. All right, let's grab another color here. Green. That would go out, and it would include 8. So 1, 2, 3, 4, 5. We're only including 5. It would get the next 3 after that. But again, we're not going to grab those because we don't need them. So we count up the number of 1s. We see that that's 2. So we need to add another 1 to make it 3. So this is our new number right here. We're going to do this all this way like this. And that's our complete Hamming code. So again, this is the Hamming code. Yeah, the Hamming code right here. So and here's the part that's cool is that we did the beginning part, and the beginning part has a lot of parity bits. But if you notice, each time that parity bit gets twice as far away. So the next one will be 16, and then 32, and then 64. So every time it doubles the number of space that it uses. And it turns out that we can recognize if one bit is wrong. So let's take this and let's practice this. Let's grab this. So I'm going to grab this 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1. So then I just take a random, I'm just going to pick one of these ones out of the middle here. Let's pick this one, cross that out, and let's say somehow miraculously that got flipped over. Okay, so let's look to see. So what we're going to do is we're going to put all of these back into, right, into that same kind of style. So then I have, this is in position. I'll go ahead and do my box again. Position 1, 2, 3, 4, 5. There had to have been an easier way to do this by copying and pasting, I'm sure. Oh wait, that's 9. Man, your professor's having trouble today. Welcome to being human. Okay, so, alright. Let's use red in here so it's a little easier to see the numbers. So 1, 1, 0, 0, 1, 0, and then this is our one that messed up. We go 1, 0, 1, 0, 1. So what we're going to do is we're going to check the parity bits, and we're going to see which ones are right and which ones are wrong. Okay. So let's look here. So 1, every other one. So 1, 2, 1, or 1, that doesn't count, right? That's nothing. So 2, 2. Oh, wait a second. It's odd parity. That is wrong. Okay, let's try number 2 then. So 2, we check this one. Says 1, nothing. Skip 2 of them. We're still at nothing. Skip 2 of them. We're at 1, I'm sorry. 2, 3. Is that right? Let's look. Skip 2 there. Skip 2 there. Oh, we skipped that one. So 1, 2. Ah, wait a second. That's also even parity. So that one's messed up. Okay. And let's look at the 4 one. The 4. All right. So 4 will be 4. 2, 3, 4. 1, 2, 3, 4. Skip, and then that last one. Okay. So 1, 2. That one's messed up too. Man, everything's messed up here. Oh, yeah. 1, 2. This should be on, right? So that's not correct. So that's supposed to be a 1. It should be a 1 there. So that one's wrong as well. Well, man, oh, man alive. Okay, let's check the 8. The 8's going to be right. Let's find out. So the 8 just says take this one and then the next 8 numbers. 1, 2, 3. Hey, that one's odd. That one's correct. Hey, we're good. So what I'm going to do now is I'm going to do this. This is in position 4. That's in position 2. And that's in position 1. So now I don't mess these up. I'm just going to go ahead and fix that and make that back into a 0. And both of these into 1s again. I shouldn't have drawn over them. So our real problem, this says, is in place 7. So it says 7 got flipped over. Make that a 1. Oops, wrong color. Make that a 1. Well, 1, 2, 3, 4, 5, 6, 7. That is the one that I messed with, isn't it? Huh. Well, that's good news. That means we did something right. Okay, so let's grab this. I want to grab this whole thing, because what I'm going to do is that works really well. Let's go copy here. Let's go down a little bit. Insert some more space in here. And paste it in. That works. Okay. So let's fix a couple things here. Let's go ahead and erase this. So that shows how to find it if indeed that should be a 1, right? Okay, yeah. Okay. So that's how to find if one of the data bits are wrong. If just one. Hamming codes are really good at finding single errors. We'll talk about that in a second. But let's look at another example. I'm going to erase this. It's all part of that other one. Okay, so. All right, let's pick a different one to mess up. Let's mess up number 4. Let's instead of messing up that one, let's mess up number 4. Okay, so number 4, we're going to flip that over. So let's go ahead and put a 1 in there. All right, now let's check these. All right, 1, every other one. So 1, 2, 3, 3. Hey, look at that. 1 is correct. 2, 1, 2. No, sorry, it's where the blue is, right? 1, 2, 3. Hey, that one's correct as well. All right, let's look at 4. So that's where the green is. 1, 2, 3, 4. Huh. Okay, that's a problem. So we can just go ahead and put that 4 down here. And then we're going to go ahead and do the 8. So is the 8 correct? 1, 2, 3. Yep, that's odd parity. So then that equals, oh, we added all those up. That equals position 4. That tells me that position 4 is out of place. And as long as it's only one bit that's wrong, we'll always be able to use that formula to correct it. So, so here's one of the things that's really neat is that if I'm going to use Hamming code, I can actually put this in hardware. I can actually just put it, like I said, directly in hardware so that when the message comes in, it immediately gets translated by the Hamming code. And the beauty of that is it allows data transfer instantly. So not over the wire, but the translation. So to go through and do a check on this is very, very quick, and I can just do it with hardware. And we'll talk about how that works out in a bit. I don't think we'll do it today, but I think you'll get the concept eventually. All right, so that equals, this equals 4, right? Let's point it out straight there. Okay. All right, so here's the problem with Hamming codes. Hamming codes assume that errors are rare. But are they? Well, they are as long as you can control the medium. But if you have a magnetic tape, or you have a CD-ROM, or not CD-ROM, that's the wrong word, a CD or a DVD or a Blu-ray, any of those kinds of physical mediums, not so much the USB drives, although it is possible on those to get this problem. What happens is when there's an error, there tends to be a lot of errors. So when that's the case, then we have to we can't use Hamming codes because they break down if there's too many errors close together. I just noticed a question here. Bashir asked, I thought we had at least 5 days to do weekly assignments. Normally that's true. This week is a weird week because of the Monday. I don't want to make it due over the weekend, though, either. and 5 days would put us at Monday. I suppose I could extend it to Monday at 5. That's fine. That isn't a problem. In fact, actually, let me go do that right now, so that there isn't an assessment on that. But there will be a new one on Monday. So let me go ahead and go in here and change this to the 12th. All right. Hey, look at that. I'm already done. So it is now due on the 12th. And that's fair. I think that's fine. If we were coming up on an exam, probably wouldn't have done that. But because I don't like having assignments due out, being outstanding at a time of being an exam. All right. So yeah. All right. So and what I need to do is I need to be better. Summer for me ended last week. So now my Fridays my schedule on Fridays is a little bit different. So what I'll endeavor to do is on those assignments, those weekly assignments, I'll try to get them out to you on Fridays, so you'll get more than 5 days. So that's my hope. In fact, I had this one prepared on Monday, I just didn't post it. So, but that's my mistake. Okay, so these errors that a lot of times we'll see in some of these mediums are called burst errors. And Hamming codes don't work for that, because if there's like let's say in this example here where 7 was wrong, if 4 was also wrong at the same time, well, let's take a look at that. What happens if I switch both of these? That one's supposed to be. Oh, that one's supposed to be. This is the error, right? And then we put this back to a 0 here. All right, so let's calculate that. Let's do that one. Error, come on. There we go. So 1, 2, 2. Okay, that means that's wrong. So 1, we get a 1 plus. Let's look at 2. So 1, 2. That one's also wrong. Right, so 2. Look at 4. 1, 2, 3. Oh, that one's right. Because see, both the 4 and the 7 were flipped. So 4 doesn't count. And then 8, we look at 8 and we count 1, 2, 3. We're good there. So then actually, this is going to tell us that the real problem is number 3. But we know, because we're the ones who switched it, that 4 and 7 were the problems. And then it looks like it's number 3, but it's really not. So what will happen is, instead of getting closer, it'll get worse. And that's because there's a burst. There are 2 that were relatively close together. As it gets farther away, it makes it a little easier for it to catch it. But if there are 2 bits that are off in a Hamming, in something that uses Hamming code, it cannot correct it. It will always make the mistake. And so we switched to some other. And the book actually talks about one called, what is it called? Reed Solomon. And there's some usefulness to look at that one. There are other ones out there. Feel free to go and look those up. We're not going to talk about them anymore in class, but they're out there. In fact, actually, probably the most interesting one, I think, at least to me, is RSA, which is named after the 3 inventors of the algorithm. It's a really, really interesting algorithm. So let me look up what is RSA. It's Rivest Shamir Adelman. I'm probably pronouncing those incorrectly, but it is named after the 3 gentlemen who created it in 1977. And this really starts off how cryptography works. Cryptography is amazingly fun, I think. But, I think there's a lot of stuff in computer science that's fun, so it's all right. So, but cryptography is really an interesting subject. how to adequately encrypt messages so that they're quick to decrypt, but very difficult to know, to crack if you don't have the key. So that, and this is what RSA does. So, and I'll leave it for you guys to look that up. RSA algorithm. Here's a quick question, a quick quiz. Does anyone know where the word algorithm comes from? I suppose I shouldn't really ask that question because it's really hard for you guys to raise your hand and say, I do. It's interesting because it's an English word, kind of, but it's used in mathematics in a lot of different places. It comes from a systematic, this is at least what the belief is it comes from Al-Khwarizmi or Al-Khwarizmi, or I'm messing it up, I'm sure pronouncing it incorrectly, but it was a Arabic author from about 1000, and that particular author wrote down specific steps on how to do some mathematical formulas, and that's where we get the word algorithm from. Is actually people mashed it up, and actually it's the proper name for the fellow that did that. It's really kind of an interesting thing, but mathematics is very steeped in the Arabic and in India as well, both. Lots of really famous, not famous, but necessarily they were doing a lot of mathematics in those areas before anybody in Europe was doing it. So I think that's just a neat little piece of history. All right, so let's move on now, and I'm going to start talking about. Now, should I go back and look? I don't want that. You guys don't need to see that. I want to go back and look at lecture 2. Boy, that's not much there, is there? Oh, yes. Aha, right here. Did I talk about him? I did not. Well, that was a mistake on my part. All right, so right in this era, in this Gen 0 here, why didn't I talk about... That's too bad. All right, so there's a guy by the name... so let's actually kind of squiggly line this or something. We're going to switch topics big time here. George Boole. French mathematician. I believe he's French. This is around 1800. I want to say 1803, but it give or take a few years. Around 1800. So he predates any of the other computers that we're talking about, with the exception of some of those calculators in Gen 0. Get that off the screen. All right, so he comes up with something called Boolean algebra. Here's the interesting thing about it. People thought it was neat and cool, and then they left it on the shelf and no one thought about it for 150 years. Well, that's not completely true, but for the most part, it just he proved this thing. He called this thing Boolean algebra. He worked for years and years and years working on different derivations and different ways to do it and different properties of this Boolean algebra. But it didn't really take off. People didn't use it because they didn't see the practical use for it. But then along comes computers, and we get into the first generation computers when it becomes electronic. Then people went, wait a second, this Boolean algebra thing, that might be actually useful here. So they started bringing some of the elements in. And if you know what you're looking for, well, even if you don't, right? I mean, you should be able to see that in computer science we use Boolean algebra, right? Because there's two choices. Either it's a 1 or a 0, or a true or a false, or really, honestly, to tell you the honest truth, it's actually high voltage or low voltage. That's all, the only thing the computer understands. And so we change it to either true or false, or 1 or 0, just so that we can understand and we can kind of think at a higher level. The computer can't do that, right? It can only think on that high voltage, low voltage difference, and that's it. Which actually, incidentally, is why we don't have Computer Space 3, is because they've had a very difficult time trying to work out high voltage, low voltage, medium voltage. You can't. It's really difficult to do that. It's difficult to do it on any kind of a scale that would be usable. All right, so we get to Boolean algebra. So Boolean algebra really has 3 parts to it. So we can take variables, and we're going to call these variables x and y. And we could continue adding them, but usually I'll use little letters like this. And then the capital letter is and. That's an operation. And I'll show you how these work. So we can have an x or y. And then there's a third one, and that is not, and also sometimes called complement or prime. And I'll do that here in a minute. Okay, so looks like candy almost. I don't know. I'm not hungry, I swear. All right, so this is how we're going to do this. I'm going to show you guys how to do what I'm going to call this a truth table. Okay, so this is what I'm going to do. So here's my inputs. X. Well, let me do this simply. So let's go like this. So here are my inputs. So this will be the x up here, and these will be the y's over here. So the x can have a 0 and a 1, and the y can have a 0 and a 1. So 0 and 0 is 0. So, okay, so the way to think about the and is both things must be true in order for it to be true. So 1 is true. So we can think, and then we evaluate it that way. So then 1 and 0 is 0. 0 and 1 is 0. 1 and 1 is 1. So we're going to build a similar table here for OR. We're going to have a lot of other things to do as well, but this is 0, 1, and this is y, and this is x, and this is 0 and 1. So this says if either of them or both of them are true, then the whole statement is true. So in this case, 0 or 0. Let's put the or here. I'll go like this. And put the and here. So 0 or 0 is 0. 0 or 1 is 1. 0, or it's 1 or 0, and then 0 or 1 is 1, and 1 or 1 is 1. Now not is a little bit trickier because we don't have 2 columns. We just have 1. I know I'm going to switch this up on you guys, but so this is not. So I have a 0 and a 1. I moved the x from on top to the side. That's okay. So then this is under not. It is just not of 0 is 1, and not of 1 is 0. Like I said, also sometimes called the complement. Or in some cases, I'll put the word prime, and I'll show you why that is. But first off, here, if I want this to be done in Boolean algebra, I just put those two letters together. So it looks like a multiplication. It's really not. It's an and. And if I want to do this, I do the or. I'm going to do a plus sign between the two. And here, if I want to do the complement, I'm going to do X, and I'm going to put a little apostrophe on it. I should make that apostrophe better. It doesn't look very good. So just a simple little apostrophe, and that tells me that it's the negation or not X. And that's the way I'll read it, is not X. All right, so let's talk a little bit about, okay, some of the different things that we can have. Identity. So the identity is 1x equals. So if I take 1 and AND it with x, what is that equal to? That's always equal to x. And if I do a 0 or x, that equals x as well. And so this is called identity. So meaning that the 1 doesn't matter, the only thing that matters is the x. And in here, the 0 doesn't matter, the only thing that matters is the x. Now, if I do this, so if I have a 0 and, because it always has to, the second thing always has to be true, since this is always false, that will dominate. And then over here, if I want to cancel this, I can say 1 or x equals, and the answer to here, right? So if either of them or both of them could be 1, so then the 1 here carries the day, and it just makes this go away. And these are called the null properties. And then there's also this, there's this one here. We go x equals x. So x and x is x, right? Because it's always the same value in both places. So whenever there's a 1 there, it'll be a 1 in both spots. So then we're okay there. And then here, the same thing, oops, not y, x or x is also equal to x. So then we go x and the complement of x. So it's the opposite of x. Right? So if it's a 1, then the other one will be a 0. So if this one's a 1, which we need it to be, right, in order for the whole thing to be ever true. So this becomes nothing, negation. So it's not possible. And then this, the complement. So one of them has to be a 1. Well, when this one's a 1, this one's not a 1. When this one's not a 1, this one's a 1. So then this says this is always true. Then we have commutative. xy equals y x, and also x plus y equals y plus x. That's also true. Get some more space. Associative. That's a good one. Okay. X and y, and that value with the z. That equals x z y. So it doesn't matter what order we do them in, as long as they're all and, we can go ahead and flip them around. And then we can do the same thing here. X plus y, or y, x or y, or z. That's the same as saying x or z, or y. And sometimes there'll be reasons to switch those around. We also have distributive. So this one is the same we would do as regular. So x or y. Oh, sorry, I messed that up, didn't I? Yep. X and y, or x and z. Oh, no, I completely did that wrong, didn't I? Yep, I did. Because this is ORing with both of these two, so we're gonna OR it like this. We're gonna OR it with this one, and then we're gonna OR it with the other one, and then in the middle we don't put a plus sign because these are going to be ANDed. We could, yeah, that works. All right, so then let's do the other one, which is on this side, y plus z. That will be x, y, or x, z. Okay. Now we get into some of the ones that are actually they're interesting. All right, x and the quantity x or y. So let's go ahead and do this distribution. That looks a lot like this, doesn't it? Okay, so then let's do that through there. Okay, so then we go xx plus xy. Then if we recall here, that xx, what happens to xx? That just equals x. This will be a good one. Let me mark this one because I'm going to want to try to prove this one. I'm going to prove this one. I'll show you how to prove it. It's actually not too bad to prove. So this really also then, because we know this goes to x, and if this is, in order for this to be true, x has to be true, so we can actually just go like this. Equals x. So if you ever see this form here, you know that we can just say x. And then we have a different form of it here. X or xy. That looks a lot like this form, doesn't it? This also equals x. Because this will only be true when x is true. And so, and we're going to go ahead and prove this. I have how much time do we have left? Well, let me do one more. So x double complement. So just like in regular speech, if you do as a double negative, or in mathematics for that matter, then this is kind of like multiplying by -1. It's not exactly the same, but it's similar. It's the same kind of concept, but it's the double negative here is the positive. So we can go ahead. The complement of x complement is just x. Okay. So let's prove this one right here. Let's give us a little bit more room here. Let me make a chart. Okay, so let's make a chart here. X and Y. X or Y. We'll go XX. And then XY. And then we can just say right, okay, so we can just do this, X and X or Y. Okay, so what we need to do is we need to come up with all the different permutations that we can have between X and Y. And normally this is done by starting at 0, 0, and then we increment Y by 1, and then we bring Y back to 0, and we increment this by 1. There's our 4 values. Okay, so X and Y, or sorry, or X or Y. So 0 or 0 is 0, 0, X, and we're just going to go down this one. Okay, so this one is OR, so then we have a 1, and then we have a 1 again, and then we have a 1 again. All right, so now X and X, so that's a 0, that's a 0, and then we have 2 1s. X or and Y, so that's a 0, a 0, a 0, because we're looking at these two, right? So that's a 0. And then we're looking at these two, so we finally get our 1 here. Okay, so now we're going to take the X and end it. So now what we'll do is this one and this one. We're going to go ahead and mash these two together. Under an AND. Okay. 0 and 0 is 0. 0 and 1 is 0. And 1 and 1 is 1. And 1 and 1 is 1. Okay. Notice that this part of the truth table looks exactly like this. Since they're equal or the same, we can say those two things are equal, just like this identity does. I'm going to do one more of these. XX plus XY, or. Okay, so I'm going to take these two columns here, and I'm going to join them with an OR. 0 or 0 is 0. 0 or 0 is 0. 1 or 0 is 1. And 1 or 1 is 1. Notice these two are exactly the same. And this one's the same as X over here, which means since their truth tables are equal, that actually proves that they are equal in all permutations of X and Y. All right, it gives me about 20 minutes to do the very last thing I want to talk about here. So the most useful thing that maybe I'll give to you today is De Morgan's. De Morgan's. Is that listed as a law or I can never remember. Does it have it? There was a chart. Where's it at? There it is. De Morgan's Law. Yeah, okay. Okay. De Morgan's Law says this. If I have two things like this, and I put a complement on it, that, what I can do is I complement the whole thing. So I'm going to flip that off, which means I just remove it, right? Because this is a complement. I could go with a double complement, so it goes away. But in order to do that, I need to flip the two things on the inside and join them with an OR instead of an AND. So it turns an OR into an AND into an OR. Okay, so let's do this a little differently. Let's say they're both, there's no complement on the outside. So then I would say this. or x complement or y complement, and then I'll put this around here and put the complement on there. The other way we can see it is x or y with a complement equals, we complement the two things on the inside, and we switch the or into an and. So if I do this a little differently, I don't put the complement there, it's x complement and y complement, and that whole thing is a complement. Oh boy, that's a lot of stuff. All right, well, let's do a truth table. X and y. Again, all the permutations. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so let's start here. Let's get this one. Let's just get x, y. So that's just an and between the two. So we get 0, 0, 0, 1. So then we'll do that complemented. So then the complement of that is a 1, 1, 1, 0. All right, that's good on that side. Let's go here. Let's go x complement. So x complement is 1, 1, 0, 0. Right, it's just the opposite of these. And y complement is 1, 0, 1, 0. Okay. So now we have to put those two together. So x complement or y complement. So these two or, all right, that's a 1, that's a 1, that's a 1, and that's a 0. So now, this side right here was this one, right? And the other side is this one. Those truth tables are the same all the way down. Look at that. We have a win. All right, so that's this version of it. Let's do this version of it. X or y. So x or y will be 0, a 1, a 1, and a 1. And so then we do the complement of that. One, 0, 0, 0. Okay, so that's the first half of it. So we're going to go ahead and circle that. That's what we're looking for eventually. So let's do the other side. So we have this x complement, y complement. We already did x and y complement here, but this time we're going to put them together using an and. So these two anded together is a 1, and then a 0, a 0, and a 0. And we notice it's a little easier because they're right next to each other. These two are exactly the same in their way they work here, in which case we're good. That means that these two are equal. How is this useful? Because each of these is I've actually used, by the way, I've used De Morgan's law in practice, in actual coding. We had a situation where we had an if structure, a bunch of if statements together. And there's certainly a style that I like that says you should never use an if statement, like ever, like none. Although in some of the most rare circumstances you probably can, but one of the things that happens sometimes, you'll have an if statement inside of an if statement. So I'm trying to remember what it was. I don't remember what the context was. We were working on something, and there was an if statement inside of an if statement, but one of the if statements had like two different parts to it, and had an or in there. Like if this happens or this happens, then I want you to go into the if statement. And then there's another if statement inside of it that said that this has to happen. So one of the ways you can kind of think about it is that if an if statement is nested inside of another one, then the first one is required, which means that you can put them under an and. So you could take those two things and put an and there. So it would only, the inside one would only happen if both of them are true. And that's exactly what and does anyways, right? So, and then I was able to create an algebra, a Boolean algebra thing. And then I was able to use De Morgan's law to negate one of the sides and flip it over, and it actually gave me something more basic. Let's I want to get a good example here, and that way I can maybe do some Boolean algebra. Do some Boolean algebra. Okay. Let's say we have this statement. We say that this or x prime y c prime or x z. Okay, so we could look at this and we say, okay, what can we do? Well, the first thing we can do is we could pull these y's out, couldn't we? We could use that distributive property to pull those out. So then we would get, and we're going to leave this alone. So then we would get y or okay, wait. Pull these out. That goes to a y. So then these two get anded together. So this quantity with that quantity. And then we're going to stay. The or is still there. X, Z. All right, so now in this case here, now we're just going to leave this y over here the way it is. Should maybe put this under a block. So we want to do that or before we do this or this. Okay, so we see in here that there's an x prime in both of them. So then we can say, well, let's pull those out. So we get x. Oh no, we're just going to reorder them because they're all in one big order, right? So x prime, z. So it doesn't matter the order. We can switch those orders around. We don't. It's not distributive. It's associative. And now this one we know is just x, the complement of x. Complement of x. And this one Do we have that one up here? Let's go up and look. We do! That's a 0. Well, do we have this one? What happens when we AND something with a 0? Oh, it just goes away. Even if it's a complement, it doesn't matter. It goes away. So we get Y or 0 or XZ. And we go back up again one more time. Oops. Where are we at here? Oh, we're looking for, wait, what's this? Some variable or 0. Some variable or 0. It's just that variable. So then we can say Y or X, Z. It's interesting. Oh, okay. Oh, I didn't do this right. Well, you got your professor making mistakes again. It happens all the time. That's why it's actually really important. We want to double check our work, right? So always want to double check our work. So, all right, this really is, we're going to take an X prime or an X complement and a Y out of both of these two terms. So then we get Z or Z prime. And then we're going to go ahead and carry this forward. So now this one, X or not X, that's equal to 1. So we have X prime, Y, and 1 plus XZ. And then this 1, anytime you AND with AND or with a 1, it just disappears. And this is what we're left with. So we simplified this into this. But really what we did is we simplified that right there and turned it into this. Right, because the back part here is the same. Nothing changed there. And if we wanted to, we could take this under a De Morgan's. Just to see if it helps. We'll find out. So we take the complement of that first thing. And then we flip this from an AND to an OR. So then we have X, Z, complement. Put those together. Complement. So I took this part here, I treat that as a variable, and I complement that side. I then flip the OR sign into an AND sign. And then I use the other side, I take the complement of that, and then I complement the whole thing. So it's flipping all of that over. This doesn't look any better than that. In fact, if anything, it looks worse. So we're just going to go ahead and stick with this one. Oh. I had some left over down here from that other one. The wrong one. All right. Any questions? I'll probably come back and we'll do one or two more algebra, Boolean algebra problems on tomorrow night, and then we'll go on and I'll start working on looking at gates in the next section. So we're slowly catching up, but we're good here. I'll wait a couple minutes just to make sure that our lag has caught up, but otherwise we'll probably be done for the night, including all my wonderful, beautiful mistakes. It's all right. It's not a problem. So, actually, let me talk about that for a second. There's an interesting thing about learning, and most of us forget about this. We forget about it as we get older. When we were little, when we were very young, we knew this. It was inherent to us. Think about how a 2-year-old learns. I'll answer that here in a second. That's a great question, though. Okay, so think about how a 2-year-old learns. Right, a 2-year-old is experiencing their world, and they have to try things. So, like maybe trying to crawl, or try to walk, or try to run. What happens? When you're first learning how to walk, what happens a lot? You fall down. Which, there's a blessing about that, because we learn to walk when we're very short, so we don't have far to fall. I think that's a wonderful thing. I always think of that every time I see a youngster fall down. Not when they get hurt, but when they fall down on their diapered bum. I always have a little chuckle because they're never really hurt, but they don't have far to fall. Okay, so, but we know that. We know that in order to learn things, we fail. And in fact, when we're 6, we have the same thing, right? When you're trying to pour some milk out of the carton into a glass. Right? That's interesting. Carton. Out of the milk jug into the glass. I don't even know if they have milk cartons anymore. I don't think they do. Maybe. So, but sometimes we spill. And what do we learn? Well, we learn different techniques and different things different techniques to help us so that we can do that properly. And if you think about that with anything, failing is actually part of learning. So it's okay that you're not good at something right away. Now, again, it's a little interesting. We pound this in with our schooling, is that we're looking for the right answer all of the time. You only can get the right answer. But sometimes getting the wrong answer is the right thing to do, because that way it can be corrected and you will learn from it. You learn from the mistakes that you make, not from the things that you do correctly. That's how life works. And that's how we all learn, but we forget about it. We forget that that's how we learn best. So it's better to embrace that. I'm not telling you should go out with the intention of trying to fail, but you will learn better through your failures than through your successes. So when you do have a problem and where you do have a failure, take that and take a moment to step back. Yeah, you can kick yourself and maybe feel a little bit that, hey, maybe you didn't put your best foot forward. But that's okay. We just go ahead and get past that. The real important thing is, what can we learn from this and how can we do better next time? That's what you need to do. That's a really great way to think about learning. And that's the reason why my grading structure is structured the way it is, because I give students a chance to have problems and not get things correct the first time so that they can learn and move forward. And that's very, very important. Okay. How would you like us to show work? So let's open up one of the assignments for assignment 2. Let's open that up here. Let's look. Okay. Convert the binary number. This is assignment 2. Yeah. Okay. To a binary number by hand. Show all the steps. So what you're going to want to do, right, is you're going to want to start like this. You're going to say 57. Oops. 57. I'm going to convert that into some binary number, blah, 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 right? So 1, 0, 0, 1, 1, 1, 0. I don't know if that's correct or not. It doesn't matter. Okay? Because you can't do the decimal place You can't do the two sides of the decimal place. So then you have to figure out the other side. And so then you say, all right, 0.54785, whatever it is. Doesn't matter what it is. Doesn't. And so then that equals who knows what it is, right? I mean, I don't know. Fine, right? It doesn't matter. So then I just combine those two together at the end. And that gives me my whole number, my complete answer. But you want to show all the steps, right? Because you wanted to like divide by 2 and divide by 2 and divide by 2. And on this side, you're actually multiplying by 2. And if you want to, go back and look at those lectures for that. And that will help you be able to do that. But I am requiring that you give me all of those steps. If you just give me the right answer, I'll probably just give you a 1. But the steps itself, because of the process, is far more important than the actual answer. Well, okay, wait. It's at least equally important. I know I'm kind of hand-wavy on that, but does that answer your question, hopefully? Is that you'll want to just take every single step and do one little bit at a time. Don't just jump straight to the answer. If you just jump to the answer, I'm not going to give you full credit. Because the process is what's important. Especially in this class, because, having the skill to be able to convert a decimal number into a binary number, it's meaningless. That doesn't matter. That's not what this is about. What this is about is understanding at a more fundamental level how binary works. And you'll only get that if you can figure out the process. So that's why I'm making that process there. Okay, perfect. All right, we're over by 2 minutes. Otherwise, we're good to go. I will be back on stream again tomorrow night. And we'll have a go at De Morgan's Law again, and then we'll get into Gates. All right. Thanks very much.